Hello, and thank you for joining me on my talk. I am Eric Andrews, and I'm going to be discussing various emerging memory technologies today. For our agenda today, we're going to take a look at the current memory architectures and overviews and briefly review the limitations that we're running into that make emerging memory technologies such an important field of research and development in the near future. We're going to take a look at three different emerging memory technologies or classes of emerging memory technologies with the various materials and operation used, the pros and cons of the various technologies, and potential uses that these technologies could fit into in order to improve computing in the future. And then we're going to close with a review of the technologies and in order to help understand. Quickly, we're going to take a look at the current memory architectures and overview. With the current architecture, the closer you get to the CPU, the faster the speed that you need to be. But because of the memories that we have, that also comes with a reduction in density. This means that the more data that is being processed, the more you need to go and access those lower speed regions. To start, you have SRAM, which is a very high speed but very low density memory system that is used in caches throughout. The typical structure for SRAM is 6 transistors and can operate at nanosecond to sub-nanosecond times. DRAM is often used for main memory, is utilized with 1 transistor and 1 capacitor as the storage mechanism for the cell. These are typically a little bit slower than SRAM in the tens of nanoseconds of access times with slightly higher density. Flash storage is really picked up in popularity in the last 15 years as SSDs have been proven to be a good speed improvement, and the cost has really come down and made it accessible in recent years. This is the first form of non-volatile memory in systems. SRAM and DRAM are typically are volatile memories that lose the data as soon as the power is turned off, where Flash retains its data. Flash is a high-density device that can scale in 3 dimensions with multiple bits per cell, with recent technologies in 3 and 4 bits per cell on the market and picking up in adoption. And then you have the very slow memories, the traditional magnetic hard disks, magnetic tapes, and devices like that are very high in density but are very slow, that are used for long-term storage. So these are the areas that we've got. But with this structure has worked for us for many years. Why are we interested in researching new memories now? To begin, we're really reaching the limitations of scaling transistors any further. Any further shrinking of the transistor feature size comes at a increasing large cost. This limits the amount of density improvements that we have with these current technologies and is limiting the future capabilities that we have. Additionally, this reduction in scaling increases the amount of leakage that the SRAM and DRAM transistors have and really increases their power needs. It used to be that leakage was a very small part of the overall power budget, but as leakage has increased and the number of transistors has increased, leakage is now becoming a significant part of the power budget and needs to be considered in various applications, particularly in mobile applications, where we really need high-speed, low-power devices. Here, non-volatile memory is an ideal thing where you could turn off the device and turn it back on. Turn off the device in order to save memory or save power, and turn it back on instantaneously in order to go back to processing whatever you need to without restoring from the slower devices that are going to really just take more power in order to operate as you go through the restoration process. Add into this, we are increasingly adding more heavy data applications. We've got artificial intelligence, machine learning, big data coming at us and increasing more and more each and every year. These are going to need more and more memory and more high-speed applications with novel solutions in order to work around power budget issues and items like this. Here, Flash is becoming too slow to be able to be used for some of these AI and machine learning applications and has no good update in place mechanism. In order to update a Flash cell, you need to completely erase the cell, which is a millisecond operation, and then program, which is a hundreds of microsecond operation, with a read that is tens of microseconds. Really, we would like these things to be tens of nanoseconds, and we don't want to completely destroy the data, but update incrementally as we go along. But really, DRAM and SRAM for the density is too expensive for the amount of memory that these new applications are demanding now. So we need new memories in order to solve these power budget issues and high speed, high density devices that we need. The first memory technology that I'd like to introduce is phase change RAM. This is made of material known as chalcogenides. They are alloys of germanium, antimony, and tellurium. There's a lot of research going into these GSTs in order to optimize speed, retention, power, temperature capabilities, all these types of things in order to help fit it into various different areas. The basic operation is that it switches between a high resistance state and a low resistance state by switching the actual structure of the material. A high resistance state has an amorphous structure of the material and is known as a reset or logic 0. A low resistance state is a crystalline structure with and is known as a set with a logic 1. In order to reset to the amorphous state, the material is heated up very quickly with a high current pulse that is translated into a high temperature and then quenched rapidly. This is a very large short current spike and typically takes in the tens of nanoseconds time scale. A set is a moderate, very long current pulse to crystallize the material. As the temperature is at a moderate temperature, the material will anneal and the crystalline structure will slowly grow over time. And this will set the cell. Because of the long nature of the current pulse, it's typically in the hundreds of nanoseconds in length in order to set the cell. A read is done by measuring the resistance, typically by sending a small current through and measuring the voltage that is generated across the device. You want a small current in order to prevent disturb because with this device, current equals temperature. The more power that is consumed, the higher the temperature. The device structure itself can be seen in the picture in the A column, where you have two electrodes connected to a phase change material and heater. This device is then connected to some sort of a selector, either a transistor or some form of a diode that can be used to select the cell and deselect other cells when the power is off. So that way you can create a large array of this and set, detect, or reset based on the region that you need. And the picture in B, you can see the relative temperature in order to melt and reset the device, or to crystallize and set the device. And then also the read required and the relative times that each of these take. Some of the pros and cons of this phase change is that it is multiple level cell, or MLC, capable. Because the crystalline and amorphous structure grows and shrinks based off of the setting, you can reduce the set and reset times in order to change the amount and give it multiple pulses in order to get it set and reset to different levels and change the resistance and detect the resistance that way. This will help make it a competing technology with flash for the density that it can do. Additionally, this is a more mature emerging memory. There are actually already several products available on the market that can be utilized by various systems. Additionally, scaling is capable down to 5 nanometers or less based on research. This makes it something that has already been proven to be possible and doable in a cost-effective way. And we've got future shrinks and capability to make it even more cost-effective. Additionally, we can stack it in 3 dimensions. Here in the top center, you can see how you can crisscross word line and bit line with the selection device in the stack. And if you continued to build on top of this with different selectable word lines and bit lines, you can see how you could select and the different memory cells and get the data from them. It is important to note that this does come at a cost of time, both in sensing and in set and reset operation, just because you have to be more careful not to disturb other cells and ensure that you have things set up properly. Some of the cons, compared to SRAM and DRAM, it does have limited endurance. It's only capable of 10 to the 9th cycles, whereas SRAM and DRAM is virtually unlimited. Because it is a temperature state change, there is thermal disturb. If you heat it too much, such as by programming an adjacent bit, you can disturb adjacent cells and cause issues that way. Additionally, the amorphous and crystalline state can shift over time as this growth front can shift. It's going to change the resistivity of the device, and it does change as a function of time. It's fairly predictable, but is going to require additional system understanding and management of this drift mechanism. And then, even though it is already on the market, there's still a lot of physics models that need to be developed, that this device is largely physically still being researched and understood. This is likely going to limit how quickly new products can come out onto the market, and can limit the cost effectiveness of the solutions, and potentially even the yields, depending upon the issues that come up with scaling. The next technology is spin transfer torquegram. This is using a similar idea as what magnetic hard drives have used in the past, of being able to change the magnetic field of a region. How this one operates is it uses two parallel plates that can have the same or parallel magnetization, or opposite or anti-parallel magnetization. These parallel or anti-parallel magnetization changes the resistance, where the parallel is a low resistance and is referred to as a logic 0, and the anti-parallel is a high resistance with a logic 1. This device typically comes with a one transistor, one cell device. There are possibilities to do multiple cells per transistor, but selection becomes a problem. It's more difficult to scale, and we will get into that in a little bit. In order to write the data, you produce opposite electrical currents. This is going to induce opposite magnetic fields and will cause different spin on the free layer, and cause the parallel or anti-parallel magnetization. This can be done in typical times as fast as 2 nanoseconds, which gives us great comparability to SRAMs. A read, you can give a small current that will generate a voltage that you will sense with some sort of a sense amp. And this is typically going to take in the single digits of nanoseconds as well. And so it can be a relatively quick device in operation. Some of the pros and cons when comparing to SRAM: it takes roughly a ninth to a third of the cell area. The limiting factor on the cell typically is the transistor, as it does need a large transistor in order to deal with the high power requirements and high current needed in order to switch the data state. You can change the write speed in order to make it operate faster. If you reduce the write speed and make the operation faster, it does sacrifice retention, which may be very beneficial in certain applications that you don't care about long retention, but limits its benefit to non-volatile caches and power off systems. You need to make sure that you're not powering off for long periods of time in order to get the data back and restore it. There is MLC capability by having parallel resistance on the same selector. This is done by having different cell sizes that are going to have different resistances, and then as you change the different cells, you basically have different resistive states. It is not as scalable in the multi-level cell as flash and phase change, so your density isn't going to get as high. It is, however, capable of very high endurance, with research showing upwards of 10 to the 15th cycles. This theoretically should be similar to SRAM and DRAM, as you're not actually physically changing the structure, but changing the magnetic fields of the device. The cons: in order to change that magnetic field, it is a very high power requirement for a write. Additionally, it is highly temperature sensitive. Not only does the resistance of the device change with temperature, but the write current and write pulse period needs to be monitored and handled properly with temperature, which can add difficulty to the device and increase costs. There's less research on 3D stacking and scaling. It does look as though it's theoretically possible to do 3D stacking with it, but again, the limitation is the selector device needs to be able to take the high power requirements that the right has. Additionally, there's a smaller resistance ratio between the high and low resistance states compared to other resistive based detective emerging memories. This translates into yield concerns. So will it be able to be scaled for cost efficiencies? Next, we have resistive RAM, which is really a large family of devices. This is different than the resistive technologies of STT and phase change, which do change resistance. Instead, this family creates a bridge or a filament based on different mechanisms that changes the resistive state. Several examples can be seen in the top right, where you have oxide RAM, where you have oxide vacancies grown into an oxide based off of the magnitude of the electric field that will produce in, say, hafnium dioxide as an example, a path of hafnium ions that will have a relatively low resistive state. Oxide charge bridge or conductive bridge RAM is similar in that you have an oxide-based cell, but instead of introducing oxide vacancies in order to reduce the resistance, you implant copper ions into it and create a filament of copper in order to create a low resistive state. In chalcogenide CB-RAM, you change your oxide into a chalcogenide material with gold implanted in order to create the filament. With all of these, you can actually have a very high resistance ratio in the order of 4 or 5 orders of magnitude difference that can really improve reliability of the device, but does actually lower the cycling endurance capability of the device. It's also going to increase the write and read time, or it's going to increase the set and reset times of the device, as it takes longer to implant all of that data. In a high resistance state is called a reset with a logic 0, in which you remove the filament or the bridge that is of low resistance. And this can be done typically in regions of tens of nanoseconds in length. The low resistance state is a set, is known as a logic 1, in which you create this filament of low resistance pathway, and can be done in tens of nanoseconds in length. There are a variety of ways of doing this, different magnitudes of electric field, or even different polarities, as shown in the figure on the left. In some cases, with the opposite polarity, they've actually been able to get resistance, they've been able to get pulse widths down in the picosecond, hundreds of picosecond range, which really makes it a compelling competitor for SRAM technologies. The structure can also be done with one transistor, one resistor, or similar to phase change RAM with some other type of selector. Some pros and cons. This can be stacked in a cross-point array similar to phase change memory. Again, this can sacrifice access times for density. It's got very good retention with up to 250 degrees Celsius demonstrated, which is better than other emerging memories have shown. You can have speeds in the hundreds of picosecond range possible, as shown on the previous slide, to help it compete with SRAM, though not with the density and power considerations as other items. Basically, the speed comes with a cost of density and power. And it can also be MLC capable. So you can change the size of the filament and therefore change the resistivity of the device and program multiple bits. Again, allowing a great density improvement at the cost of access times. The cons: this is one of the newer mature technologies that is immature. There's a lot of materials to be considered that is going to take time to research and understand. So there's a lot there to be done. It does have better endurance capabilities than phase change, though it's still moderate. You are changing the physical structure of the device and limiting yourself that way. Some potential uses: you can put it in on-chip cache with non-volatile SRAMs or even standalone caches, saving space and potentially increasing the capacity of the cache. Here, STT and resistive RAMs are better suited for these caches based on speed requirements. You can do main memory replacement or enhancements by increasing capacity, reducing refresh requirements, going for a more mobile-friendly setup. And here it just depends upon what design considerations you've got and the cost of the system. PC RAM could be good for a hybrid setup with DRAM in order to have less standby power needs, less leakage requirements from the DRAM, with higher capacities for things like artificial intelligence. Or resistive RAM may be a good option for mobile applications. You have SSD improvements where you could utilize some of these technologies as a flash replacement or augment the bulk flash SSD by adding one of these as a cache in place of the DRAM or the log sector of the flash. Here, PC RAM and resistive RAM could be beneficial based on the density and cost. And you can enable fault-tolerant exascale computing, where you can be more resilient to soft errors that are introduced with the reduced feature sizes of SRAM and DRAM. A review of the technologies. This is a quick table to review the density, speed, power, both dynamic and leakage and volatility. That is typically based for the devices. There's still a lot of research and to be done, and this table can change, but it's a good source of reference to kind of see where these different technologies may augment and support one another, or be able to replace entirely based on the system needs. Finally, we have the updated memory overview to kind of see in a pictorial way what the previous graph was showing of the various speed and densities that these devices can have. Finally, I have the list of references used throughout the presentation and as resource for preparing for this presentation. At this point, I'm going to open it up for any questions, and thank you for the time.